All right, it is time to talk about electrostatics. This particular chapter is broken up into 3 different lessons: general information, specifically how charge is transferred from one object to another, and then just some details and a couple of equations for calculating the strength of the electric field. Today, we're just going to cover some general information about electrostatics. So the first thing that we need to know is that all conversations about our electrical charge today are primarily going to be about the electrons. So the word electrostatics is officially defined here as the study of electric charges at rest, but we're specifically going to be talking about the collection of electrons in order to give us our electric charge. We could have an abundance of electrons, we could have a deficit of electrons, and so that's ultimately what's going to determine what our electric charge is. So when we say the study of electric charges at rest, we're really focusing on the collection of electric charges or electrons on a particular object. Here we just want to take a moment to review the subatomic particles of an atom. You are expected to know that protons and neutrons are located in the nucleus, and we are going to expect you as well to know that protons are positively charged. Now, none of our answers, none of our discussions are going to be about altering or manipulating any part of the nucleus. We are not adding or removing protons. So really, I just need you to be aware that that's where the positive charge comes from on our atoms. Our electrons are found on the outside. This is really the focus of all the things that we're talking about in this course. So electric charges are created because of when and how the electrons move. We've already talked about how electrons can move in order to create photons or light, and we will continue to talk about the movement of the electron, which ultimately determines the electric charge of our material. It says here at the bottom that there's usually an equal number of protons and electrons in an atom so that there's no net charge. So generally speaking, we start off learning in chemistry about the periodic table and how we can use that to give us information about the neutral version of an atom. And so that's kind of the concept that I want to just briefly discuss here. If we have an atom that is neutral, what that means is that it has the same number of protons and electrons. Well, in our class, we're not going to be talking so much about individual atoms, but we're going to be talking about an object or a material which is made of atoms. So it's going to follow the same concept. If we have a same number of protons and electrons, what that means is that every positive is canceled out with a negative. Every negative is neutralized by the positive, right? So having the same number of pluses and minuses is really the main idea that we need to move forward in our conversations. I'm actually going to be redrawing this little plus minus thing in order to talk about some more vocabulary for us here in just a moment. But for right now, it's important that we understand neutral meaning same number of positives and negatives or pluses and minuses. All right, so when we talk about the electric charge, we have an actual value for that electric charge, and that's going to be something that we can actually quantify for both our protons and our electrons. I want you to take a look at the numbers here, and hopefully you easily recognize that they have the same value for both our protons and our electrons. Both of them are 1.6 times 10 to the negative 19 coulombs. The only difference is that electrons are negatively charged and protons are positively charged. This letter C here at the end is our unit, and it is a capital C to represent a coulomb, and that is the unit we will be using to measure all electric charges. So going back to that conversation about objects are typically neutral, in order for us to have these electric charges that I was talking about, at some point they have to have a different number of pluses and minuses so that they're no longer neutral. And so whenever we have an atom that doesn't have the same number of positives and negatives, we refer to that as an ion. So again, we're going to be talking about full objects in our class, but it follows the same concept because everything is made up of atoms. So looking at this slide here, we are going to discuss the vocabulary word ion. The purpose of the ionic bond at the top of the page is really just a little refresher. We have covalent and ionic bonds, and the main idea that I want to review with you is that when the sodium and the chlorine combine, they combined because the sodium was looking to lose an electron, which would leave it positively charged, and the chlorine was looking to gain an electron, which would leave it negatively charged. So we called this an ion simply because we had positive and negative, or in general just charged atoms at the end as a result of this compound forming. And so the first word that you actually need to make sure you understand and learn from this slide is just the vocabulary word ion. So an ion is going to be an atom that has an electric charge. And so notice that this first definition for the word ion, it's not specific. If it is charged, it is an ion. And so that's the first vocabulary word that we need to understand. Now, if we look at the two words below that, they both contain that root ion. So these are going to be the specifics for identifying whether it is a positively charged thing or ion, or whether it is a negatively charged ion, okay? So now we're gonna take a second and we're gonna look at the explanations to the right of each of these vocabulary words and make sure we understand how is it that the ions are created and how are we supposed to know if we're given a story or we're given an illustration whether or not that object ends up as a positive charge or as a negative charge. So again, we're going to say that we're assuming that all of our objects start off neutral. So I'm just going to give us some pluses and minuses here so that we can work with them visually. Let's talk about the statement here for the cation. It says that these are atoms that are lacking electrons. So we have an object, maybe it is something that you are holding in your hand and you are sitting all warm and cozy in a blanket and it's kind of getting moved around on top of the blanket. And then after sitting there and kind of moving around for a while, your object in your hand is no longer neutral. So what happened to it? What kind of charge does it have? And how is that even possible that it now magically has a charge? Well, it's very simple. If the movement that you were putting that object through caused the object itself to lose some of its electrons, so let's say that these electrons got removed, got pulled off of that object that you were holding. Now, if we look at the illustration, if we remove those electrons, we now have an excess of positive charges. But since it's not about the protons moving, we've rephrased the statement here to not say that we have more positives, because that's a little misleading sometimes. We're going to say instead that it is lacking those electrons. It lost electrons, so it now has fewer electrons, and so by default, that is going to leave our object positively charged. So that's why there's a plus sign here. Now, how can you remember that the vocabulary word cation belongs to the positive charged ion? Well, one suggestion that I have for you is by simply looking at the letter T in the middle of the word cation and simply thinking of it as a plus sign. This is one very simple way that you can remember that the vocabulary word cation belongs to the positively charged material or atom. On the other side, if we are going to gain electrons, so now we have an excess, that is going to leave us with a negative charge. So once again, if we start off with a neutral material, so same number of pluses and minuses, and then now my object is going to pick up electrons, so electrons are going to come from some other place, and they are going to now live on our object that we were holding in our hand. Now I have an excess of those electrons, which means that overall I have more negatives, so my object is now going to be negatively charged. So how can we remember that the word anion belongs to a negative charge? Well, if we just simply think about the English language, that an prefix is there to give words a negative meaning, right? A negative interpretation. So these are a couple of ways that you can remember cations are positively charged, anions are negatively charged, and you absolutely are going to need to understand how did that happen and how can we express what took place in terms of our electron movement in order to create those different charges. This is just another suggestion for those of you who like more creative interpretations here of a way that you can remember, because cats and paw, so cats being positively charged, that's just another visual here for you, okay? All right, so now let's talk about the interaction of our charges. As I said before, our ionic compound tends to be one positive and one negative because of a very basic understanding that oppositely charged things are attracted to each other. So here we need to know if I have two objects that are of opposite charges, they are going to be attracted. So what this means is that they are going to want to move towards each other. They want to be closer. They're wanting to come together, okay? So when you see a picture like this in the future on, say, maybe a quiz or a test where you have some illustrations to interpret for the question, I want you to see this single arrow here as representing the direction of the desired movement. So one positive, one negative, they desire to be together. They are attracted. They want to move close to each other. If we look at the pictures above that, we're now looking at two charges that are the same. When we say like charges repel, that word like means that they are of the same charge. So two positives or two negatives. The word repel means that they want to separate or they want to move away from each other, okay? So now when we look at the illustrations below, these arrows here are to indicate that these objects desire to move in opposite directions. They are trying to get away from each other or separate. That's what we mean when we say like charges repel. Okay, so this is an interaction that we're going to need to understand for future conversations, okay? This is just a different set of visuals for those of you who like to see things depicted different ways. And so now we're going to talk about the concept of conservation of charge. We've talked about conservation of various things throughout our science lessons. And so the main idea is that whatever our topic is, it is not created, it is not destroyed, it simply transfers from place to place or from form to form. And so I like to say that conservation of anything means that the total amount doesn't change. So today we're going to talk about conservation of charge. So what we're saying is that the total amount of charge available between our two objects that are interacting, that total charge never changes. All of those electrons are always accounted for. It's just that they may be collecting on one object in the beginning of the scenario, and then maybe they've distributed themselves differently and they're collecting more on a different object later on in the story because of their interaction, right? So here we're talking about the law of conservation of charge. And again, that charge specifically is going to be explained by simply focusing on the movement or arrangement of the electrons specifically, because it's the electrons that move around on our atoms. So we have a couple of different illustrations here, and they're basically both showing the same concept. I want to take a second and just make sure that we understand how we're supposed to interpret these illustrations. You guys will have a variety of questions. Maybe you're drawing pluses and minuses as your answer. Maybe you just get a picture like this and then you're asked questions about it. Or maybe you're just given a statement, no illustration, but you still need to be able to visualize what does that actually mean in terms of my charges. So here on the left-hand side, I want to make sure that everybody understands that the purpose of only putting plus signs on this rod is simply to illustrate that it is, generally speaking, positively charged. It doesn't mean that there are no electrons there. Remember, the electrons are going to be on the atoms, and all atoms have some protons and electrons, right? So they're simply showing an excess of charge so that we understand the rod is positive. If we look at this sphere here, it tells us that the charge is 0, but if that notation wasn't there, we should be able to see from the picture that every plus has a negative. They're all paired up. It's the same number of pluses and minuses. With this arrow here, they are showing me that the electron is moving from the sphere to the rod. So when we look at the after picture, what we see is that the rod has now become more negative. In this case, it's still positively charged. We went from a positive 4 to a positive 2, but it's getting closer to that neutral or negative value, right? On the other hand, we have what was a neutral sphere that is now positively charged. Again, they give us the notation here, but if they didn't write that on the screen, we should be able to see that we do have some pairs, but we have a couple of positives that are left without that negative to neutralize it. And so that's what we need to be looking for if we're forced to interpret our charges strictly from our illustrations. Down here, I want to point out that we have some explanations that go with the illustration. So in this case, these are two neutral objects. Okay, so right here we start off with two objects that are initially neutral. And then what we see on the after side is that we have very few negative charges here on this cloth. I only have 2 of them, okay? And I definitely had more than that to begin with. So what I need to grasp, kind of big idea here, is that some of these electrons left. And because the cloth is interacting with this rod, then we should correctly assume that the electrons moved onto the rod. So if the electrons moved onto the rod, that leaves my rod negatively charged because it was originally neutral, and so now it has an excess. That by default is going to leave the cloth positively charged because now it is lacking. It lost electrons. So this is just a different way, different phrasing that we can use to explain how we're supposed to know if objects are positive or negative in charge, okay? All right, the last thing that we need to discuss here is the math that corresponds with today's lesson. So we have talked about how opposites attract and like charges repel. So if I have 2 objects that are brought together and then they desire to move toward each other or away from each other, well, technically, there is a force that's going to act on them in order to bring them together, attraction, or push them apart, repulsion. And so we can calculate the strength of that force by using what is called Coulomb's law. So Coulomb's law is an equation that's going to explain why do our objects look like this? Well, it all comes down to there is a force that's either trying to push things away from each other, like these poor children's hairs, or trying to bring things together, like that cat that is just covered in those little styrofoam balls, right? So let's look at the formula. Here is our equation. F equals KQQ over D squared. We've seen equations similar to this in the past, specifically dealing with the universal gravitational force law. So what we need to review here is some things that we should already know. Capital F always is going to indicate a force. Remember, lowercase f is frequency, so please make sure you're writing it correctly. Forces measured in newtons. We should all know that by heart by now. Then we have our displacement or distance, and we're going to have that listed in meters. If it's not, we will convert it. And then be very careful with this equation. We had an equation similar to this in the past, and I gave the same caution at that time. This formula says that I'm going to take my distance and I'm going to square that value. So please make sure that you do not forget the squared in your math work. Now let's look at the letters that we don't already know. This letter K is what we call Coulomb's constant. So K is going to be a set value that you are simply going to put in every calculation. If we are asking you, what is the value for the force, or what is the strength of the charge, or what was the distance between them? If you're doing actual math work where we're calculating newtons, meters, coulombs, we've got to put this number in, okay? Please make sure that you write it down and make it a point to learn that value. 9 times 10 to the 9th. So that brings us then to the letter Q. So the letter Q, if you notice, is in the equation twice. Well, that's because we have two charged objects. So when you are filling in your givens into the equation for your Coulomb's law, you have to have both Q's. If you're finding that you only have one, you need to go back and read the problem. Either they're asking you to solve for the other electric charge, or you missed something somewhere, because Coulomb's law has to show the force between two charged objects. And that is going to be measured in a unit called coulombs, and it's a capital C. And for right now, I just simply need you to know that the unit for electric charge is coulombs, okay? So we're going to be very careful in our math work here. If you recall, when we were working with the universal gravitational force equation, we would also ask you questions like, what kind of relationship do force and charge have? You need to know that they are directly related. You need to know that force and displacement are inversely related. There is an inverse square relationship, to be exact. And so that's kind of what we are reviewing with the first couple of bullets here. So how am I supposed to know whether things are directly or inversely proportional? All right, this is a little trick that I showed you guys, and I want to take a second to review. K, Q, and Q, those are all in the numerator. Force is a whole number. So if it were written as a fraction, it would just be over 1. It is in the numerator. So whenever your two variables are set equal to each other, they have to be on opposite sides of the equal sign. If they are both located in the numerator, so force and charge are both located in the numerator, that is going to make them directly related. So if I increase the electric charge, I'm going to get a stronger force. That sounds like common sense when I say it, right? But this is how we can use the formula to help us know that. If we are talking about our displacements, that is going to be in the denominator on the right side. So if we are being asked to compare the force to the displacement, one is in the numerator, one is in the denominator, so that is going to make them inverse. But be careful, we have to make sure that we always square that value. So I actually wrote this as the inverse square relationship, okay? So what this means is the greater the distance between our electric charges, the weaker the force is. And hopefully that also kind of just sounds like common sense. Now, how we answer these questions about if I double the distance, I'll get 1/4 of the force. Let me walk you through that really quickly. If we are using our equation and we are not changing values, we will just put them as a 1, meaning it's the same as the original. If they are asking me to double my distance, instead of putting a 1 as the letter D, I'm going to put that as a 2 because that would be doubling it, right? So I'm going to put a number 2 here, and then the formula says I have to square that. So this is going to be a 2 squared. Now I just want to simplify this fraction. Multiplying across gives me 1. 2 squared gives me 4. There is nothing left to simplify here. So my force is going to be 1/4 of whatever that original force value is. It is going to be 4 times weaker, okay? Any fraction answer that you get means that it's a weaker force. Any whole number answer that you get means that it's going to be a stronger force, okay? All right, the last thing here, I have a couple of questions sprinkled throughout the chapter where I will simply ask you with your math work, was that an attractive or repulsive force? Here it says if we're analyzing the force value, a positive answer means that it was a repulsive force and a negative answer means that it's an attractive force. Honestly, that just feels backwards to me, although it is correct. So rather than trying to remember whether a positive or negative force is an attraction, what I prefer to do is to just look back at my scenario. If I had two positively charged things, well, my answer is going to be a positive number. And so that means that these objects are going to repel. And that's why we see positive means repel in this statement here. But I like to think of it as because I have two charges that are the same. If I have a charge that is positive mixed with a charge that is negative, that's going to give me a negative value for my force, and opposites attract, so that means it's going to be repulsive. Again, I only ask a couple of questions where you are expected to know whether the force is attractive or repulsive, so I just wanted you to have a couple of ideas as to how you can go about forming that answer, okay? So again, this was just an introduction to electrostatics. It's all about how the electrons are arranged, where they are located, so that it either creates a neutral, a positive, or a negative charge. And this formula is simply to tell us about how we can decide what the values are for all of the parts involved.